All right, electrical power. So we already learned about power before in terms of mechanics, and it's really the same concept, but here we're just applying it to electrical circuits. So power is energy consumed or transferred per time. So we know that energy can't really be created or destroyed, but it can change form, it can transfer from one thing to another. So when we talk about power, we're really talking about how much energy either got transformed into some other form or transferred from one thing to another in a certain amount of time. So how quickly is that energy being used up? The units are joules, which are energy, per second, which has a special name, watts, which we write with just a W. So joules is the units for energy. Seconds is the normal units for time. Joules per second has a special name. It's a watt. This is the same set of units as we had before. Voltage, you might remember, is energy per charge. And the magic square, as we go from potential energy to the per charge relationship, we get to voltage. In the same way that the electric field is the force per charge, the voltage or the potential difference or electrical potential, those are all the same thing, is energy per charge. And current is, so this is joules per coulomb or volts. Current is charge per time, coulombs per second, or amperes. So, voltage is energy per charge, joules per coulomb. Current is charge per time, coulombs per second. So our units, if we take a volt and we multiply by an amp, that's like saying we have a joules per coulomb times a coulomb per second. Cancel out the coulombs, that's a joule per second, or a watt. So when we multiply the units of voltage by the units of current, we end up with the units of power. So the equation for power is, it's the voltage times the current. Because that's basically just how the units work out. Volts is energy per charge. Current is charge per second. So when we multiply those two things, we get energy per second, which is power. Okay, this is not the only equation for power though. We can use this equation together with Ohm's law to write it in a few different forms. So Ohm's law is R equals V over I. We already did this before, where you can write any one of these three variables by itself, V equals I times R, or I equals V over R. Is that off the screen? No, okay, good. So any of these three equations are just a different way to write Ohm's law. They're this same relationship, R equals V over I. To get from this one to this one, we just multiplied both sides of the equation by I. To get from here to here, we divided both sides of the equation by R. But these three statements are the same relationship. So what this means is if we want to write power equals volts times current, instead of volts, we could write I times R. So we could replace this V with I times R because that's the same as V. So then we would have I times R times I again. That's I squared R. Or if we wanted to get rid of the I, we could keep the V, and then instead of I, we could write V over R. So that would be V times V over R. That would be V squared over R. So any of these three expressions are equal to the power. If you know 2 out of the 3 of the voltage, the current, or the resistance, you can use one of these 3 options to calculate the power. Or if you wanted to go the long way around, say that you had the current and the resistance, but not the voltage, and you didn't want to use these ones, you could use Ohm's law to find the voltage from the current and resistance, and then plug the voltage and the current into the power equation. But really, we have this equation, and all these other things are just rearranging the variables to help you put them together. This is on the reference table. These ones are not. All of these options are listed on the reference table. Okay. So work is basically the amount of energy transferred. So its units are joules, because it's basically energy. So, to find the relationship between the power and the work, power is energy per time. So you could do power equals the work divided by the time. Or another way to write this is that the work equals power times the time. If you make $12 per hour, then to find how much money you made, you need to multiply by hours. If we're consuming 20 joules per second, we need to multiply by seconds to find the amount of energy. Same idea. Per basically means that we need to multiply by that. So to find the energy, we take the power, we multiply by the time. And then there's other ways to calculate the work, but really it's just doing this same strategy again of coming up with different versions of the equation by combining things together. So work is the power times the time. That's sort of how power is defined. But because it's the power times the time, we could also take any of these expressions and multiply them by the time, because VI is the same as power, I squared R is the same as power, V squared over R is the same as power. So I could write VI times T, or I could write I squared R times T, or I could write V squared over R times T. Either way, I'm taking the power, any of these powers, and multiplying it by the time. So depending on what things you know, you can use any one of these options, and these again are all listed on the reference table. All right, let's see some examples. So, So a light bulb is connected to a 120 volt outlet. So V equals 120 volts and uses 15 watts of power. So that's P equals 15 watts. We pointed this out before. It's kind of an annoying thing. This W is the units of watts. This number goes in for power, not work. The units of work are joules. The units of power are watts. It's unfortunate that they have two different uses for the W, but this goes in for the power, not the work. And A wants to know how much current flows through the light bulb. So I'm going to use P equals V times I. 15 watts equals 120 volts times I. And then to find I, I'll divide both sides by 120. And I get 0.125 equals I. It's a little hard to figure out the units from your actual calculations here, but because our answer is the current, that means that the units are amps. So this is the answer. B wants to know what the resistance is. We now know voltage, power, and current. So we have a couple options to find the resistance. We could use this equation, or this equation. Probably the easiest one is this one because it's already solved for R. Oops, I guess you can't see what I'm talking about. Ohm's law up here. So we have this one, or this one. We know all the things in all these equations. So we could choose which one we want to do. Any of them would work. Let's do this one. So I have R equals V over I. The volts is still 120 volts, and the current is 0.125 amps. So 120 over 0.125 is 960. And the answer for resistance should be in units of ohms. Just as an experiment, we can try one of these other ones. Let's say that we forgot that Ohm's law existed and we were just looking at the power. We also know that the power equals I squared R. So I could have put in 15 watts equals 0.125 amps squared times R. And if I were to solve for this, I would get the same answer, 960. Okay, let's see another example with work. This question says, a phone battery stores 15 kilojoules of energy. Alarm bell's going off here. I have a metric prefix. I'm going to need to convert units. If it charges in 3 hours, what is the power consumed while charging? And then if the voltage is 5 volts, what's the resistance? So I know that it stores this much energy. Where does this fit into the equations? This is a work. Because it's an amount of energy, it's in joules, that's work. So my work is 15 kilojoules. But I want to put this in the normal units, so I'm going to convert to joules. Kilo means 1,000. So 1 kilojoule equals 1,000 joules, and this is 15,000 joules. That's the work. Then I also have 3 hours. So the time is 3 hours. But I need to convert this to seconds. So 1 hour is 60 minutes. and then 1 minute is 60 seconds. Or you can just know that there's 3,600 seconds in an hour. Hours cancels with hours, minutes cancels with minutes, and our answer will be in seconds. 3 times 60 times 60 equals 10,800 seconds. So we had to do some unit conversions, but we got the work and the time from the question. And the first thing it's asking is, what is the power? So I have work equals power times time. 15,000 equals power times 10,800. I could write the units, but I wrote them over here, so it's okay. 15,000 divided by 10,800 comes out to about 1.39. That's the power, and the units of power are watts. So not very much. It should make sense that the amount of energy required to charge your phone is less than a light bulb. The phone's pretty small. It doesn't get really hot while it's charging. It might get a little bit warm. Okay. Now we want to find the resistance. We could do the same thing. We have our same choice of different formulas. We know the power. We know the voltage. Oh, we don't know the current actually. So we're going to need to use the power and the voltage to find the resistance. So the equation that relates those three things is P equals V squared over R. Our power is 1.39 watts equals 5 volts squared over R. The variable that I want to solve for here is on the bottom of the equation. So I'm going to multiply both sides by R. 1.39 R equals 5 squared is 25. Divide both sides by 1.39. And I should get R equals 17.98, or I'll just round up to 18. 18 ohms. Now, I put resistance in quotes here in the question because it's not a resistor, it's a battery, and the resistance that we're talking about is kind of a question of how difficult is it for the charges in the battery to move around back to their higher energy position. So it's not exactly what we would normally think of as the resistance like in a wire or in a resistor, but it's still a quantity that we can calculate based on the formulas that we have. All right, hope that was helpful. Give the examples a try. Reach out to me if you need any help. Hope that you're having a great week.